This video is going to briefly explore a fundamental concept in statistics called the central limit theorem. This topic will build on some of the concepts that we covered in our videos on variance and random sampling. In our refresher video on the concept of variance, we looked at how one can describe how spread out a distribution of individual scores are by calculating its variance. In our video on random sampling, we covered how the mean and variance of a population of scores can be estimated from the means and variances of random samples selected from that population. We also discussed the concept of the expected values of those statistics and demonstrated that in the long run, the average of an infinite number of sample means or variances taken from the population will be equal to the population values. These discussions focused on two of the three characteristics of distributions: their level and their spread. The level of a distribution refers to its midpoint. The mean, median, and mode are familiar measures that are used to describe the level of a distribution. Our previous videos focused on the mean. As you know, the spread of a distribution refers to how spread out or scattered the values are. In our video on the variance, we focused on the variance and standard deviation as the most important measures of spread. In our video on random sampling, we also looked at the range of means as another measure of spread. In this video, we will continue our discussion of the level and spread of distributions, but we will also be discussing the third characteristic of distributions, the shape. The shape of a distribution refers to the pattern or form of a distribution and can take many forms. A distribution can be symmetric, like the normal distribution, skewed, bimodal, as a few examples. The central limit theorem is concerned with the characteristics of a particular type of distribution, called a sampling distribution. As the name suggests, a sampling distribution is a distribution of sample statistics calculated from random samples taken from a population rather than the individual scores themselves. For instance, let's assume that we have selected multiple random samples of scores of a certain sample size from a population. Then we calculate and record the mean of each one of the samples. If we compute statistics such as the means of these random samples, we can create a new distribution that is called a sampling distribution. It is a sampling distribution because it contains statistics like the mean, calculated from multiple samples rather than the individual's scores themselves. In this example, we are creating a sampling distribution of sample means by using the means of each random sample obtained from a larger population of scores as the elements of the distribution. We now can examine the properties of this sampling distribution. As with distributions of individual scores, sampling distributions can be described by their level, spread, and shape. In our video on random sampling, we focused on level. We showed that when you take a very large number of random samples from a population, calculate the mean of each sample, and then average those means, the result will be equal to the true mean of the population from which those samples were drawn. In this video, we are going to focus on the other two characteristics of sampling distributions, the spread and the shape. As with individual scores that form a sample, a distribution of sample means will also exhibit variability. That is, not all the sample means will be identical. They will differ from one another. Just as we can compute statistics to describe the spread or variability of individual scores in a distribution, we can compute statistics that measure the variability of these sample means. Just like we do with distributions made up of individual scores to describe how spread out those scores are, the standard deviation can also be used to describe how spread out the means are in a sampling distribution of means. When applied to a sampling distribution of sample means, this statistic is called the standard error of the mean, or simply the standard error. While students sometimes find the name confusing due to the inclusion of the word error, it is important to note that error in this context does not indicate any mistake or error was made. Instead, it refers to the average difference between each individual mean in the sampling distribution when compared to the average of all the means. This measure allows us to assess how widely the individual means vary in the distribution. In statistical language, the disparity between any score in a distribution and the mean of that distribution can be referred to as error. In an upcoming video, we will explore this idea in greater depth, providing a more comprehensive discussion of the concept of statistical error as it relates to analysis of variance. There are two different notations used for the standard error of the mean, depending on whether or not the true population standard deviation is known. If the population standard deviation is known, the standard error of the mean is notated as sigma sub x bar. However, in practice, the standard deviation of the population is rarely known. So the standard error of the mean is notated as S sub x bar to indicate that its value is based on the standard deviation of a sample, S. In either case, the x bar subscript indicates that the standard error is an estimate of the variability of sample means, not individual scores. We're now going to show you how to calculate the standard error of the mean. The formulas for calculating the standard error of the mean are simple. They are either sigma sub x bar equals sigma divided by the square root of n, if the population standard deviation is known, or S sub x bar equals S divided by the square root of n, if the population standard deviation is not known and the sample standard deviation is being used as an estimate. In both cases, n is the size of the sample being used to calculate the standard error. So let's get started with our discussion of the central limit theorem. As in our other videos, we will be using statistical simulations to demonstrate the important concepts. These simulations will cover the shape, spread, and level of sampling distributions when the populations from which they are created are either normal or non-normal. So let's begin by looking at how we are going to create a sampling distribution to analyze. We will start by looking at the shape of the sampling distribution, and then we will move on to the spread. For our first example, our simulator has been populated with 1,000 normally distributed scores that have a mean of 100 and a standard deviation of 15. We will start by drawing 100 random samples of size 40 from this population. At the bottom of each column, you can see that we calculated the mean standard deviation and the standard error of the mean for each sample. We will not have enough room to display all 100 samples on the screen at one time, but here are what the first 30 random samples look like. The first question we want to answer is what the shape of the distribution of sample means will look like. The central limit theorem states that the distribution of sample means will be normally distributed if the population from which the samples were drawn was also normally distributed. The simulator will create a histogram of these sample means so we can answer this question. Let's start by examining the shape of the population distribution. As you can see on the histogram, the population distribution appears to be normally distributed. Now we are going to take 100 random samples of size 40 from the population and plot the means from all the samples. As we run the simulator, pay close attention to the histogram of the sample means. We will overlay the histogram with a normal curve, which will help us visualize how closely our sample means align with a normal distribution. Let's now turn our attention to the histogram of the sample means. Look at how it takes the shape of a normal curve, even though it's created from the means of multiple small samples. Let's also examine the standard error of the mean. Because we are using our simulator, we know that the population standard deviation from which the 100 samples were drawn is 15. Therefore, we can use this value to calculate the actual standard error of the mean in the population for a sample size of 40. You can see that this value is 2.37, which is simply 15 divided by the square root of 40. But we can also calculate the standard error of each of the 100 random samples that the simulator has drawn from the population. This value is recalculated each time a new set of samples is drawn. Like we did in our video on random sampling, we can look at the standard error for each sample that has been drawn and see that they vary from one another as you would expect. But because we are drawing 100 random samples of size 40 from the population each time we take a new sample, we can examine what the average standard error is across all 100 samples and compare that to the standard error of the mean calculated using the population standard deviation to see how close the values are. As you can see, the average of the standard errors across all the samples is very close to the standard error of 2.37 when calculated using the population standard deviation. This demonstrates how well the standard error of the mean calculated using a single sample will reflect the population value in the long run. What you should also observe is that the standard error of the mean is much smaller than the standard deviation of the scores in the population. This indicates that the spread of the distribution of sample means will be much narrower than the spread of the distribution of the scores from which those means were calculated. Finally, observe how close the average of the sample means is to the actual population mean of 100 as you would expect. This is the central limit theorem in action. The distribution of sample means tends to approximate a normal distribution when the population from which the samples were drawn was also normal. Now we will rerun the simulation multiple times. Notice that as we rerun our simulation with new random samples, the distribution of sample means always approximates a normal curve. Regardless of how many times we run the simulation, the pattern holds. The distribution of sample means approximates a normal distribution. We have been exploring the central limit theorem using a population that was normally distributed. Now we are going to look at how the central limit theorem behaves when our underlying population deviates significantly from normality. As before, we'll be using our simulator to demonstrate the important concepts. The population that we used in the demonstration that you just watched was normally distributed with a mean of 100 and a standard deviation of 15. For this demonstration, we've transformed that normal population into a non-normal population by taking the sign of each of the 1,000 scores. We then scaled this new population so that it also has a mean of 100 and a standard deviation of 15, just like the original population. However, unlike the original population, this transformed population is no longer normally distributed. Look at this histogram. You can clearly see that the shape of this new population looks nothing like the shape of our original normally distributed population. So the question is, what will the shape of the sampling distribution of means be if we draw random samples from this non-normal population? As before, our simulator will draw 100 samples, each of size 40, from this population. For each sample, it will calculate the sample mean, the sample standard deviation, and the standard error of the mean. Just as we did with the normal population, we will generate a histogram of the sampling distribution of the sample means. Now look at this histogram of sample means. Even though the underlying population is clearly not normal, the distribution of sample means still resembles a normal curve. This is the power of the central limit theorem. Regardless of the underlying shape of the population distribution, the distribution of sample means tends to approximate a normal distribution, given a large enough sample size. Generally, this will be true so long as the sample size is 30 or greater. You can also see that the other statistics calculated from the sampling distribution still demonstrate the expected outcomes. The average of the sample means still is a good estimator of the population mean, and the mean of the standard error of all the samples is very close to the standard error calculated using the true population standard deviation. As we did in our last demonstration, we will now repeat the simulation a number of times so we can examine the shape of the sampling distributions that are created from 100 random samples of size 40. You will see that most of the resulting distributions generally have a normal-looking shape, but as you would expect, due to sampling fluctuation, some of the results look more like a normal distribution than others. Notice the standard error values. Just like in our previous example, the standard errors are much smaller than the standard deviation of the population, indicating that the variability of the sample means is less than the variability of the population. Also, as we said, the average of the standard errors of the samples will closely match the theoretical value calculated using the population standard deviation, reinforcing the robustness of the standard error of the mean as a statistical measure. So let's summarize what we have covered so far in this video. The central limit theorem tells us that the means of a sufficiently large number of samples from any population will approximate a normal distribution, regardless of the shape of the population distribution. The distribution of a group of statistics calculated from random samples taken from a population forms a sampling distribution. If the statistic calculated is the mean of the samples, then the sampling distribution is called the sampling distribution of sample means. The means included in the sampling distribution will vary due to normal sampling fluctuation. The standard error of the mean gives us a measure of how much our sample means are expected to vary. The simulator demonstrated that the calculated standard error of the mean, based on a group of samples, will align closely with the theoretical value calculated using the usually unknown population standard deviation. The variability of sample means, as measured by the standard error of the mean, is always less than the variability of the population, as measured by the population standard deviation. In this video, one of our focuses has been on the standard error of the mean, but we haven't said anything about its connection to ANOVA. This connection may not be immediately obvious, but it is very important. In our discussion of sampling distributions of sample means, you learned that when you take a series of random samples from a population and calculate the mean of each of the samples, those means will vary due to normal sampling fluctuation. A measure of the amount of variation is provided by the standard error of the mean, but it is concerned with the variation of means instead of the variation of individual scores. As you will learn, one of the basic calculations that is done in analysis of variance is the calculation of the variance of the means of the groups being compared by the analysis. This is because at the population level, the larger the differences among those means, the larger the variance of those means will be. On the other hand, if there are no differences among the means, the variance of the means will be zero. This is, of course, at the population level. The means of the samples that are actually being evaluated in an analysis of variance will reflect, but not be exactly equal to these population values due to normal sampling fluctuations. Here's a small example to show how analysis of variance uses variances to draw conclusions about means. On the screen you will see a table that contains the hypothetical means of 3 groups of scores and the variances of those means. Let's look at the first row. The mean of each of the groups is the same, it is 100. The last column displays the variance of those 3 means. As you would expect, the variance is 0 because the means do not vary. They are all 100. So if the only information you were given was that the variance of a group of means was 0, you would know that the means must be equal to each other. Let's now look at the other 3 rows. In row 2, you can see that the means are very close to each other, but they are not equal. Therefore, there is a very small amount of variance. In this case, it is 0.22. In the 3rd and 4th rows, the means are much more different from one another. As you can see, the larger the difference among the means, the larger the variance becomes. We can't tell which of the means are different or what caused them to differ just by looking at the variance. But if there is any variance among the means, we would know that they must not be equal to each other. This is the process that analysis of variance uses to draw conclusions about mean differences by examining variances. The job of analysis of variance is to determine whether the differences between the sample means, as reflected by their variance, is large enough to rule out random sampling fluctuation as the cause of the differences. This is the basis of how analysis of variance draws conclusions about the differences between means by analyzing variances. There is a second related connection between analysis of variance and the standard error of the mean. As you will learn in more detail in our video on ANOVA, obtaining an unbiased estimate of the population variance as part of the analysis is required. We are now going to show you how the standard error of the mean is mathematically related to the variance of the population itself. It turns out that the formula for the standard error of the mean can be algebraically rearranged to provide this unbiased estimate of the population variance. We are going to show you that relationship now. First, let's review the formula for the standard error of the mean. It's simply the standard deviation of our sample, S, divided by the square root of the sample size, n. The standard error of the mean is an estimate of the standard deviation of the sample means. But in analysis of variance, we are interested in the variance of the sample means. Because the variance is simply the square of the standard deviation, if we square all the terms in the formula, the result will be the variance of the sample means, s squared sub x bar. Now we can multiply both sides of the equation by our sample size, n. The result of this operation shows that the sample variance, s squared, is equal to the sample size, n, times the variance of the sample means, s squared sub x bar. Now let's take this a step further. You learned in our video on random sampling that the sample variance of a random sample is an unbiased estimate of the variance of the population from which the sample was drawn. Therefore, we can substitute the population variance, sigma squared, for our sample variance, s squared, in the equation. This gives us a new equation. N times s squared sub x bar is equal to sigma squared. This tells us that the variance of the sample means, multiplied by the sample size, provides an unbiased estimate of the population variance, sigma squared. This process demonstrates how we can use the variance of the means of samples to arrive at an unbiased estimate of the population variance. This concludes our video on the central limit theorem, sampling distributions, the standard error of the mean, and their connection to analysis of variance. We hope you found our presentation valuable. Thank you for watching.